Okay, now let's do a little projectile motion with math. Let's do the math that goes with it. So now our objectives are going to be to sketch the theoretical path of a projectile, recognize the independence of the vertical and horizontal motion, and also solve problems involving projectiles filed both horizontally, which is a cliff problem, and also at an angle. Now, projectile, by definition, is anything that's been acted upon only upon gravity after it's been thrown. We'll ignore air resistance in this course, and then usually projectiles are launched at angles, although there are cases where they're not. Generally, if you think about it, kicking a soccer ball, you kick it at some angle. Hitting a baseball, you hit it at some angle. Serving a volleyball, you do it at some angle. Golf balls usually done at an angle. Now, the path of a projectile is called the trajectory. And once launched at an angle, it's going to move in parabolic arc. And understand that the time up is equal to the time down, and that's kind of important, the fact that happens. If a ball takes 2 seconds to reach the top, it takes 2 seconds to reach the bottom. Good. Second thing is, since it's going to take the same amount of time going up and the same amount of time going down, the velocity at the start and the velocity at the finish are exactly the same. Now, when you launch it at an angle, you're going to have motion in 2 dimensions. The vertical is going to act like free fall, and the horizontal has got 0 acceleration. There's no unbalanced force acting in the x direction. So therefore, I can completely treat them independently. So now, Joe throws a baseball horizontally at 42 meters per second from a height of 2 meters. How far will the ball travel before it hits the ground? So let's draw a little sketch of what's going on. Okay, there's the thing. It's being launched at 42 meters per second that way. That's v in the x direction. The path of the ball, let's do the path of the ball in black. It's going to be a parabola like this. What I'm trying to find is, what is that direction? I'm trying to find x. Now, the key thing is, I know this distance here is 2 meters. So kind of like a riverboat problem, we're going to do each part of it independently. The first thing I need to do is figure out how long it's going to take an object to fall 2 meters. So the equation for that is going to be x is equal to VIT plus 1/2 AT squared. Now, for a cliff problem, and this is a cliff problem, and the fact that you're launching something horizontally, and that's the key, I'm simply going to say that y, and I'm going to use the letter y, is equal to 0, because there's no initial speed in the y direction, plus 1/2 AT squared. Now, the nice thing about that is, if you rearrange that equation, you get t is equal to 2y divided by a, and then it's the square root of that. Prove to yourself, do the math and prove to yourself that that actually works. Okay, that's going to allow me to calculate the time it takes to hit the ground. Similarly to how we've calculated before the time it takes a boat to get across a river. So now, for this case, I'm going to say t is equal to 2 times y, which is 2 meters, divided by 10 meters per second squared. So when I do this, I'm going to have the square root of 4 divided by 10, the square root of 0.4, and the square root of 0.4, I don't know off the top of my head, so let's check a calculator. So this is going to take 0.63 seconds. So it takes 0.63 seconds to reach the ground. If it takes 0.63 seconds to reach the ground, the next thing I have to do is figure out how far it's going to travel. Since there's no acceleration in the x direction, I can simply say Vx is equal to dx over t. So therefore dx is equal to Vx times t. So x, which I'm looking for, is equal to v in the x times t. So 42 meters per second times 0.635 is equal to 26.6 meters. By the way, this is actually similar to a person throwing a baseball, and that is a realistic number at that speed and that height. 2 meters is about your average 5'7", 5'8" person throwing. Okay, let's try some more. Now, if I have a parabolic path, that's what a cannonball looks like fired off a cliff. When it says which point has the greatest horizontal velocity, key thing to understand here, and this goes back to our understanding of it, is that is going to be the same in every case. The horizontal velocity is not going to change. The vertical velocity is going to change. Now, if you have an angled projectile, the first thing you're going to have to do is split it up into Vx and Vy. And we're going to treat those components independent of one another. And the key thing to understand, just to give you a reference point, without air, maximum angle is going to be 45 degrees. And we're going to test that in class to see what we get. So now, label Vx or Vy for each point. And then where's the maximum speed and where is the minimum speed? Okay, pause your thing for just a second and see if you can do it. Okay, if you're back now. Well, let's go through and let's do Vx first. That's Vx, that's Vx, that's Vx, that's Vx. Those should all be the same length. Now, Vy, it takes a little more thought process. As it's going up, what's going to happen is if that's your initial, well, your initial Vx would be the component of that that's pointing in that direction, so it would correspond to that. This is going to be shorter than that. Right up here, Vy is equal to 0 momentarily at the top. Over here, it's Vy is now pointing down, and then here Vy is pointing down, but even more. That length here should be the same as the initial length there. Now, when it says where is the maximum total speed, the maximum total speed is 2 points. Right as soon as it was launched and as soon as it hits the ground. Those are going to be the same. Projectiles are symmetrical. So max, V is here and here. Minimum speed is where I have the lowest possible speed, and that's going to be the point where I only have the x speed, the minimum, and the top of that is what we call hang time. That's the lowest part. So let's go ahead and write that so it's in your notes. That point is the minimum speed right there. Okay, now you're usually given the initial velocity and an angle, and then you're going to need to separate it into Vx and Vy, and there's all sorts of spare writing there, but we'll just write over it. So this is usually given. Then they also usually give this. Then what you're going to have to do is separate into that. That's Vx. Vx is going to stay the same. This is Vy. Vy is going to change. But it changes because of gravity, so therefore we can do it. Now, play around with your trig functions and realize that Vy is the opposite side, Vx is the adjacent side. we usually know this value. We'll just call it V. Well, let's call it V total to kind of help us differentiate. And Vx is the adjacent side, so therefore it's cosine. So Vx is equal to V times the cosine of the angle theta. Vy is equal to V times the sine of theta. Now, those equations won't be given to you, but you need to be able to know that. You need to be able to calculate it. Now, let's look at a sample problem. We have Fred the Undead, and he's a non-human cannonball. He's a zombie. And he's launched at an angle of 30 degrees with an initial speed of 26 meters per second. How far will he fly before reaching the ground? Now, I'm going to give you the steps. We'll do the rest of it in class, but I'm going to give you the steps. Number one, first thing we need to do, separate Vx and Vy. Need to have that. Critically important. Number two, use Vy to find half time. In other words, you can use Vy to figure out the time to the top of the arc. And kind of the important thing to realize is at the top of the arc, there is no Vy. So Vy essentially goes from whatever the initial Vy was to 0. So it goes from initial Vy all the way to 0 at the top. 3, double the time you found. So double the answer you got for number 2. Then 4, use Vx and t to get x. Now, we'll do the math of this in class, but I want you to understand and have a framework for doing it. I hope this helped.